Welcome to Module 3, Chapter 7, Polar Coordinates, Polar Graphs, and Vectors. This is some of my favorite stuff. We definitely do this in Calculus BC. Let me show you your calculator first to let you know that you do have a polar mode. So if you hit mode on your calculator, and most of you are in functions, which is typical y equals, x squared, stuff like that. If you go to parametric, there's some interesting graphs there. And if you change it to polar, something interesting still. R equals, in this case, you have equations in terms of cosines and sines and different things. And R stands for the radius or the radial line from the origin out to a point. And you're going to plot all those points. We'll trace a graph here in a minute. But one of the graphs that I like are those two equations that you can see that this is 0 to 6.28, which are radians. And I noticed that my calculator was in degrees. If I were to hit graph, I might get a funny picture. So one thing that I want to do is match my mode. And I think I'm going to leave it in degrees so you can see it's easier to trace. So I want to go a full circle. So not 0 to 2 pi, but 0 to 360. You can count by whatever the step is what you want to count by around the circle. This window is okay. It might be a little small, so I could possibly go to Zoom Standard, Zoom 6. It will give you kind of a smashed looking graph, and you can play around with the window. Or you could hit, after you did Zoom Standard, you could hit Zoom Square, which really gives you a more accurate squared up 1-to-1 aspect ratio graph. And you could even zoom in and see, this is just kind of a cool graph. If you hit enter right there, it zooms in closer. It's interesting to watch it graph. It's not a function. It is kind of graphing lines out to, or points out to, here I'm going to scroll around the blue rose shape is what that's called. And really what it is it's going out from the origin out to this point. So this radius is right in here, that line. And then as you move around the shape, that radius is getting smaller or bigger depending. But it's always coming back to the origin. And that angle right in there is, supposed to be at a 37.5 degree angle, and you're counting out a certain radius. Here, let me change the format to polar graphing coordinates and show you what that does on the trace. So we saw that was like a 37.5 degree angle, but now you see that the radius, or that length from the origin, is measured at a 1.03-ish. Or here at 30 degrees, the radius is 2. And you can go back 15 degrees, the radius is much longer. So you're now plotting points, r's and thetas, instead of x's and y's. They still have an x and y, and you will be asked to convert those. Their conversion formulas I'm going to show you right now. But that's kind of fun that you could do it on the calculator. So when I hit trace and I go back to that 15, there's the x coordinate over 3.34 up 0.89, and the radius from the origin is, you saw before, was about 3 something. So what we're looking at is kind of every single point here has these relationships. In other words, this point is of course xy, like we remember, normal, but it also has a certain angle and radius to get there. So there's 2 ways to get there. You could either do red or blue. So this particular picture is kind of like the poster child for polar and vector and actually parametric equations, because everything it's a right triangle. And if you wanted to convert back and forth, the equation for x actually comes from cosine, where x over r, the adjacent over the hypotenuse, is equal to cosine theta. When you cross multiply, you get r cosine theta. The one for y is the same way. It's just y over r. That would be opposite of this angle over hypotenuse, and that's equal to sine. And so when you cross multiply, you have y is equal to r sine theta. And incidentally, these are the components for vectors. So to go to vector mode, I would just come up here and draw an arrow. And you're like, woohoo, there's my vector. Okay, so the X and Y coordinates then would have a little bit different flavor. They would actually have like these V for vectors on the sides, but you would still write it as the ordered pair. And now we just turned in a point on a polar graph. We turned that point into an actual vector that points to that point. And they're the same ordered pair. It's the same X and Y, which is kind of cool. Of course, another dominant relationship out of this picture is that x squared plus y squared is equal to r squared. You can never get away from Pythagorean theorem. And if you do tangent of the angle, it's going to equal y over x. So that's SOHCAHTOA. If you want to solve for theta, you will do the tangent inverse of y over x on your calculator is fine. And you'll add pi when you're either in the second or third quadrant, which really means that you have a negative x value. So if you have a point that's over here in the negative x, you're going to have to, whatever this angle is, you're going to have to add pi to that, or 180 degrees, depending on when you're on what you're in. But the Alex will have you working through some really cool graphs, I hope. I mean, these graphs are really nice. And also showing you how to convert those coordinates. And then you'll get into some vectors here. Let's just click on this one just to see what kind of graphs that you're in for. Of course, they do a circle, which is boring, r equals 2 in polar land. And here they have a different circle, and they're showing you those points that I was showing you. Yeah, those are kind of boring. Let's see. Ooh, there's a cardioid. This is a sideways. It looks like a heart shape. And there's equations for that. This is a spiral, or no, same cardioid, sorry. But you can have some spirals and different things. This is an upside down cardioid. They do go through the calculator, which is nice. They show you how to plot. This is called a limacon, and it has like a loop-de-loop. So there's a loop-de-loop inside another one. So these graphs are really quite interesting. Here's a rose that I did. Oh, I did do that one. I didn't mean that to do the exact one, but if you do sine, the orientation's a little bit different, and I actually overlapped a couple of those. So here are the classical curves. You don't have to memorize these or anything, but it's fascinating to be studying this really different type of mathematics in a course like this, pre-calc. You don't get that till pre-calc. So enjoy these graphs. Good luck.